Natural language processing is absolutely booming because we create a lot of language data. Google has a $1 billion NLP model right in front of you. If you turn on captions, it knows what I'm saying. Am I happy? What language am I speaking? These are some of the questions that NLP will answer. So today, we start using NLP to answer these questions using Python. We'll make a machine learning model that can accurately predict whether an email is spam or ham. It is a classic NLP problem, and it is a really good one to start with. I promise that this video will be explained clearly and concisely for you to understand. You're going to get through the video and feel like you've learned a lot about NLP, and you will have. Okay, well, I'm super excited. Let's get started. I'll see you in there. This tutorial will be using the spam classification dataset available at this Kaggle link. We start by loading this into a data frame with import pandas as PD, make a data frame df, make that equal to pd.readcsv, and then pass the name of the file. Then we'll output df.head. If you get this error, make sure you download the CSV file from the website and then upload it over here. If everything's correct, you should see this data frame with these are category 1s. All of these emails are spams. This is an email that has this message and this is the name of the file. We've marked it as spam. Same with these other 5. If we instead look at df.tail, which is the last 5 rows of the data frame, we can see all of these ones are not spam. We can count how many rows are spam and not spam with df subcategory, that gets that column, and then .value counts to see we have 3,900 not spam messages and 1,896 spam messages. We will try to make a machine learning model that can classify, given just one of these new messages, whether it is spam or not. The main library we'll be using is called NLTK. So we'll import NLTK, which stands for Natural Language Processing Toolkit. We need to download 2 things from NLTK. We need to download WordNet and stopwords, which we'll see shortly. There's many standard processing techniques for text, and we'll look at them one by one. It all starts with something called tokenizing. So we'll make something called a tokenizer equal to NLTK.regulareExpression tokenizer, and we're going to pass this. Starting with tokenizing, we're going to perform many different transformations to this test message, which is just an example email. It's a string with a bunch of weird stuff in it, and we're going to transform this. It's easiest to show what tokenizing is by doing an example. We do test message tokenized, and we'll set that equal to tokenizer.tokenize the test underscore message, and if we output that result, we see that we now have a list of strings, and actually we call each of these strings now tokens. Basically, they are still kind of words, except they're not necessarily words, because HTML here, well, that came from this. It's not really a word, it's more of a token. That's what we're going to call it. Now, essentially, this tokenizing just preserved the order and kept what's important in this message. Grabbed hey, and then there's comma, comma, space. Let's just separate that and bring it as hey. This GG thing, and then a space. Okay, let's put that in as GG here. Feet, white space, let's just put it in feet, and so on. It's going to ignore these brackets, these question marks, and sort of weird stuff like this. Something that gets annoying very quickly is if we have uppercase letters and lowercase letters, or maybe even a combination of both. Something very easy is just to convert everything to lowercase. And we can do that with this list function right here. If we do t.lower for t in test message tokenized, that's just this list right here, we convert all of the different strings to lowercase, and then we return it as a list. Test message underscore lowercase is equal to this thing. If we output that, then we will see the same thing, but everything in lowercase. Now, it's important to note that we're deciding to lowercase everything, and we're deciding to tokenize everything with this tokenizer. In NLP, there's many different choices for processing. These are just some very common choices. Another very popular processing technique is called lemmatization/stemming. If we do from nltk.stem, import this WordNet lemmatizer. So we're doing lemmatizing, not stemming. It's something very close, but slightly different. We will make a lemmatizer equal to a WordNet lemmatizer. Very similar to the lowercasing example where we went through every token and we applied some function to that token to make a new token. We're going to do the same thing here, except we're going to make the list of lemmatizer.lemmatize t for t in test message lowercase. So we go through each of these different tokens and apply lemmatizer.lemmatize to that token. Let's see what that does. If we make this list a variable, we'll call it test message stemmed, or actually it should be lemmatized tokens. And we set that thing equal to the list we just created. And if we output that, what we have here is that hey actually stayed the same. It was hey before. The GGs actually stayed exactly the same as well. But here we have feet, and that got converted to foot. That is because they really mean the same word. They are just slightly different in that feet is plural. It means multiple feet, and foot is just 1 foot. Why would we want feet to be converted to foot? We're trying to extract meaning out of this text, and if we understand that it's about feet, well, then we don't care really whether it's 2 feet or 1 feet. See also that the bads just got converted to bad, but for some reason randoms stuck as randoms. There's words in in here that aren't really useful, like it. Pretty much every email, or at least the vast majority, are going to have the word it in there. So this is what we call a stop word. It stops our text from being useful. So we'll do from nltk.corpus import stop words, which is just a list or a set of words that we really don't find useful. Because this is all in English, we are going to set stop words equal to stopwords.words with English. So only English stop words like it and to and from and how and all of that stuff. Sticking with the same pattern as before, we want to check if each of these tokens is or is not a stop word. We can do that with making the list of T for T in test message not stemmed tokens. Sorry, that should be test message lemmatized tokens. If T not in stop words, going through each of these words, only keep it if it's not in stop words. If it's not in stop words, that means it's a useful word. If it is in stop words, we don't want it. We'll of course make this a variable and we will call it test message useful tokens, set that equal to the list, and if we output that, then we will see the exact same list, except it's going to be missing words like it. I think that's actually the only word it removed. Although we won't do it for our problem, it might be useful sometimes to add your own sort of stop words convenient to your problem. You might want to filter stuff out that's not helpful to your text. Aside from one more, which we'll see later, these are all the processing techniques we're going to use for converting a message to a list of tokens. These are still called tokens. The first thing was just called tokenizer because it's literally just converting them to tokens, but all of these things, we consider all of these just processed tokens. We can do all of those at once. It's going to look confusing at first, but it's simply a function that converts a string, which is a message, to a token list, gets tokens, which calls the tokenizer.tokenize on the string. Lowercase tokens, t.lower for t in tokens, lematizer.lemmatize t for t in lowercase tokens. And then finally, if they're not in stop words, we want to keep them. Only keep what we'll call useful tokens. This function will be extremely useful to us. Now, since this function is doing the exact same thing as the above, if we do message to token list, call that function on the original string, that test message, we better see the exact same result here, which we do. We're just partitioning the data frame into two different pieces for train and test. We'll do that first with shuffling the data frame by setting df equal to df.sample, frac equals 1 with random state equals 1 so that you and I get the same results. Indices get messed up, so you have to do df is equal to df.reset index with drop equal to true, split index. We set this equal to the integer of the length of data frame, so however many rows that we have, and then times 0.8. This then gets an index that corresponds to the 80% point. The first 80% can go to train and the last 20% can go to test. If we do train df and test df, train df is equal to this piece, df colon split index, and then test df is just split index onward. There's again a nuance with the indices getting messed up, so we have to do train df equal to train df.reset index with drop equal to true. That's exactly the same thing with test. Train df and test df as a tuple like this. This piece is train df. It's the first 4,636 rows. Test df, the remaining 1160 rows. Something we'll soon find tremendously useful is the count of all the different tokens that are in our training data frame, of all the different messages that are in the training partition. So right here, this message, that message, or whatever ones that are in the training data frame, we're going to tokenize each and every one of those lines, do all of our processing like the stop words, lemmatization like before. I'm going to go through that whole list of tokens, count all of the different unique tokens, and get a frequency of all of the tokens. So we'll start with a blank dictionary. We'll call this token counter, and then we will say for message in train df sub message, go through each and every message in the train data frame. First, need to tokenize that message. We had this function called message to token list. Converts that message, this should be message, sorry. We convert that message into a list of tokens, doing all that processing as before. This might look confusing at first, but I'll explain it. We just do for each token in the messages token list, if that token is in the token counter already. Well, at first there's nothing in it. It'll do else token counter sub token is equal to 1. If we haven't seen the token before, just set the count equal to 1, saying we've seen it once before. For any token we have seen before, okay, we'll just add the count to 1, meaning that we have seen it again. We'll first just output the length of this thing, saying how many different tokens are in the whole column. We see a number 86,415 unique tokens. We do not want to use all of those for our machine learning model. We're going to pick, maybe 10, 15, 20, 100 different features instead of have 86,415 of them. If we output that without the length, we will see this absolutely massive dictionary with all of its different counts. HTML appeared 4,175 times, this font thing 35,000 times. Many of them appeared much less frequently, like business info only appeared 6. We only want what's really popular because they aren't stop words. This stuff is probably useful to our problem. And if it's not, well then you might want to go through by hand to just get rid of that and add it to our stop words. Let me explain a very useful function called keep token. Keep token takes a process token, so just something like this, like website or compromised, or maybe something that's not even in this thing here, and a threshold, which is a positive integer. If process token is not in the token counter, okay, that token counter is that exact same object here. If we are seeing some sort of token that is not even in this thing, we do not want it. So we return false. Otherwise, so we take token counter, we know that it's at least a valid key because we already checked if it's not in that token counter. We input it here and get the count. See how many times did we see that in our training information. It's going to look up the value here, which is a count. Unless we saw it at least 10 or 50 or 100 or 1,000 times, we don't want to keep that token. For example, we can call keep token with, say, this token random. And have we seen that 10 times? Yes, we have seen that 10 times. Have we seen it 20 times? Yes, we have. Maybe 100 times? No, we haven't. So we can play around with this threshold value, see what we want to keep depending on how much we've seen each word. Now this part is slightly confusing, but stick with me here. We get features equal to a blank set, and then for token in token counter. So we go through each of these different keys in our token counter. If keep token with token and then 10,000 as the threshold, have we seen this token 10,000 times? Then we will add that to our features set. It turns out that with the threshold of 10,000, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different tokens. They are the most popular tokens to occur. We are going to assume that they are useful features for describing whether an email is spam or not spam. Soon making a machine learning model based off of counting how many times this token occurs, how many times this token occurs. We call this a bag of words approach. It's a bag because we don't really care about the order of the sentence. We just calculate how many times does this occur, how many times does that occur, and each of these different ones. We are first going to convert features into a list, the list of features. That way it has some very obvious order to it. So it decided to have HTTP, then TR, then size, and so on. Don't worry about the code here quite yet. Token to index mapping. It's going to take this as a token and make a mapping to an index out of it. This is the 0th spot in the array, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9 spot. Map the key to its corresponding index. At the 3rd spot, so 0, 1, 2, 3, we see that. B is the 9th spot, and so each of these we can map the token to its corresponding index so that we can just look up this token and add to the count in a particular spot. We will make a count vector where it's this 3rd index spot that will represent the count for 3D, and then the 9th spot that will represent the count for B. In a moment it'll all make sense. Let's look at an example. Message to token list, that's just our token processing function of this random email. Then as before, we would tokenize it and get some tokens that we care about. 3D, we decided we care about that. B and BR we do, except this thing in here bad. Well, that's a token that we don't actually care about. We're not going to bother counting for it. We want to get the count of HTTP. It showed up 0 times. So in that spot, well, the 0th spot, we put a 0. Same thing for TR. That did not show up at all. Put a 0 in that spot. Size didn't show up as well. 3D, well, we saw that once, and so we put a 1 there. Font, we see that twice, so that'll be 2. And BR, we saw that once, and so on. That is called a bag of words vector or a bag of words representation. So let's write a Python function that can take a message like this. We're going to get its corresponding count vector that looks like this. We're going to import numpy as np, and then we will make a function message to count vector, which simply takes a message that is going to be a string. We're going to initialize our count vector equal to the numpy.zeros of length of features. Make it a vector of 10 different zeros because at first we haven't seen anything at all. Since we're taking in the raw message, we tokenize it with processed list of tokens is equal to message to token list, that same processing function, and pass that the message. I'm now going to paste in a confusing block of code. Don't worry, I will explain it. For each token in process list of tokens, so we processed our tokens and it looks something like this. For each of those tokens, if that token is not in features, well, features is that list of tokens that we actually care about. If that token is not in features, then we don't care to count it, we discard it with continue, move on to the next iteration of the loop, grab the next token. Otherwise, if that's not true, then we saw some token we do care to count. We get its corresponding index, because for whatever it is, we need to map it to its particular location here. So we grab the index with token to index mapping sub the token. Then we just do count vector sub index, up that by 1. And so if it's size, well, we'd get the index of 2, and we'd say count vector sub 2, or this spot is going to go up by 1. That is going to be our corresponding count vector, then return count vector. Then we do message to count vector of that email, we should get its corresponding vector. I see from off screen that I actually had a very slight error here. We'll match up with very close, except here it actually claims that there is 0 TDs, which of course is the correct one. By using pandas and this function, we can actually do message to count vector, that function, train_df message.iloc some integer. Here, if we do sub 0, this passes the first message in the training data frame so that we get its corresponding vector out of that. I bet you this email is spam, with not train_df sub message.iloc sub 0, but train_df.iloc 0. We can see the category is 1, meaning it is spam. I can also show you right here as a wild guess the 66th message with all these different counts. I bet you this one's spam as well. If I do 65, yep, that message is spam because it has all of this weird stuff in it. All of the features that we used here, HTTP, TR, size, 3D, this is mostly just HTML tags. And why are those showing up in an email message? And so if we have a vector that has a lot of these counts, I'm gonna guess it's spam. If we looked at sub 3, this one, mostly zeros. If we do sub 3, that one is not spam. We now have a function that can convert a message into its corresponding vector representation. We really want to do that for each message in both the training data frame and in the test data frame. We also want each of those vectors matched up with whether it is spam or not spam, normally in machine learning called xtrain and ytrain, where xtrain is our matrix of inputs. It's going to have rows where each row its corresponding vector, and ytrain is going to be whether that vector is spam or not spam. We need xtrain, ytrain, xtest, and ytest. We are now going to make a function past either the train data frame or the test data frame. It gets NumPy arrays. This is the last function we're going to write ourselves. Going to paste it in and explain each piece. df to capital X and Y. So this is going to get the X part as well as the Y part. So we pass in this thing dff. So we get Y equal to df subcategory. Just convert that whole column to a NumPy array and then make sure it's only integers. So it's either 0 if it's not spam or 1 if it's spam. Then we get this variable equal to the message column. Count vectors is this thing we're going to build up. It's a list that's at first empty. We're going to go through and get the count vector for each of the messages. For message in the message column, count vector is equal to the message to count vector. That's that function we just created over here. Then we just do count vectors.append with count vector. We add the message's count vector to that list. And so in order, it's going to match up with Y. And at the end, we can just set X equal to the NumPy array of all the count vectors. And then again, making sure that those are integers. So we will just return X comma Y. Xtrain, Ytrain. We call this function passing in train_df, and then the same thing down here, test_df instead. We do xtrain.shape, ytrain.shape, get xtest and ytest, get both of their shapes. We should see xtrain shape. Well, 4636 matches up here because that's however many emails that we had in the training data frame. And xtrain, it'll have 10 columns here because we decided that it's going to have 10 different counts, 10 different features. And then the same thing, except we only have 1160 observations in the test set. Something very standard for all machine learning is doing some sort of preprocessing or scaling method. From sklearn.preprocessing, import the min-max scaler. So we'll make a scaler, the min-max scaler, and then we'll do .fit with the xtrain. So xtrain, xtest is scalar.transform, xtrain, and scalar.transform, xtest. We just transform both of those input arrays. For example, xtrain, well, then it looks like the numbers are all closer to 0. That's pretty much what it's doing. Alas, we are finally ready to make a machine learning model, and trust me, it's going to work pretty well. From sklearn.linear model, it's always good to start with this one. Import logistic regression. Okay, remember this is a classification problem. It is either 0, not spam, or 1, spam. So we're doing a classification model, and so we should also look at classification metrics. Like from sklearn.metrics, we will import classification report, basically a bunch of metrics to report on a given model. We will make a logistic regression, we'll call it LR, equal to, and then we fit width, we need to pass it both xtrain and ytrain, fit these features that we were learning over here, all of these different vectors, how do these match up after transforming them to ytrain? How do they help us predict ytrain? We can see how well it does on the test set. So we print the classification report as ytest. We need to predict lr.predict using xtest. How well is this going to accurately predict the test set of information? We get an EOF while parsing, which is really just boring. And so we can see here, and actually a pretty good model. I'm not going to explain all the metrics here. If you want to see the metrics, well, I have a video for that, binary classification metrics, but we can see here our model is, decent. I'm not going to dwell on this and instead just show you the exact same thing. I just pasted in a bunch of code. It's just making a random forest instead of a logistic regression classifier. We'll make that, it looks exactly the same, fit it on xtrain and ytrain, and see how well this model does. A random forest does a little bit better. We'll see a macro average F1 score of 80 instead of 67 here. That is much better. This code is in the description of the YouTube video. Of course, take a look at that if you want. And if you are willing, there's a nice exercise you can do by playing around with the threshold value way above. So we decided that this threshold should be 10,000, which yielded only the top 10 recurring features. Play around with this value and see if it's more features helps, maybe less features helps, and try to get different accuracy measures here, as well as definitely if you want to understand these metrics, check out my binary classification metrics video. That will be very helpful for that. If this video was helpful to you, please drop a like. I would really appreciate it. And if you're not subscribed to my channel, well, I'm going to be making a ton more content on NLP in the future, as well as everything machine learning. I am always doing that. Thanks so much for watching, and I'll see you next time.